Hello and welcome to the second video in the root finding methods series. In the previous video, we talked about the initial guesses required in both the bracketing and open methods. In this video, we will see how we can automatically estimate the interval containing the root of a function. In general, if a function f of x is real and continuous in the interval from xl to xu and the corresponding function values have opposite signs such that their product is less than 0, then there is at least one real root present in this interval. Incremental search uses this observation to locate intervals where the function changes its sign. Then, from these intervals, we can provide effective initial guesses to find roots. We will now try to program the increment search, and the problem we'll use is about finding the roots of a quadratic equation, which is x squared minus 7 times x plus 10 equals 0. Typically, we can use the quadratic formula to find the roots of this equation. And we know that this function has two roots, one at x is equal to 2 and the other at x is equal to 5. Let's write some code to visually inspect the function. In cell 2, we write the function f that takes an argument x and outputs the quadratic equation response. And we also have a function to return the solution using the quadratic formula. For the sake of visualization, we define a range of x values in cell 3. In cell 4, we plot the function as well as the corresponding roots. In cell 5, we use the quadratic formula to compute the roots, which we can verify are at x is equal to 2 and x is equal to 5. So the goal of the incremental search is to output the number of roots present and the corresponding intervals for each root. Let's next see how we can do this using a Python code. An important factor in the incremental search is the increment length. If it is too long, closely spaced roots might be missed, so we have to set it carefully. The evaluation interval to start and end the incremental search must also be set carefully. This is the function that performs the incremental search. It takes the quadratic function, the start and end values of the evaluation interval, and the increment length as its arguments. We create the x values using NumPy's arange method, which outputs an array that starts at xstart and ends at xend, and the delta x between the two values is the increment length. We compute the function values for the given values in the X array. Then we check if one of the values is already a root. If we are lucky and find some of the roots immediately, we store them in the intervals underscore in list. Then for the other remaining values, we use the product criterion between the two consecutive values to find the root interval. If we find more roots, we'll store the corresponding intervals and then output the total number of roots and the corresponding intervals after combining the results from intervals underscore in list. In cell 7, we apply the incremental search on the example quadratic equation. And we can see that the function outputs correctly the intervals that contain the roots at x is equal to 2. In cell 8, we plot the intervals containing each of the two roots. These are the intervals that we obtained using the incremental search. As we saw, incremental search can help us identify the intervals using which we can carefully select the initial guesses for the bracketing and open methods. With this, we conclude this video. In the next video, we will look at the bisection method in detail and find the root values in these intervals. Thanks and see you in the next video.